welcome back. We're going to continue our discussion on configurations, in particular R and S. Now, previously in Chem 330, we looked at determining R and S configurations, but we were only limiting our discussion to line structures. This time around, we're trying to convert line structures to something called a Fischer projection, but the idea of how we determine R and S stay the same. Okay, so without further ado, let's get into this topic. Now, there will be a sequence of material, all sort of related, like going from line to Fischer, line to Newman, Newman to line, and stuff like that. Okay, now you may wonder, what does this all mean? I think you really have to understand organic chemistry, not just from a three-dimensional perspective, but also from a two-dimensional perspective, because let's face it, 99.9% of the time, actually I should say 100% of the time, when you're taking a test or any other situation, you're never ever going to be holding a molecule that's three-dimensional. So that's one of the reasons. The second reason is, if you plan to sit for any professional exam, like MCAT, any of the other ones, you would definitely encounter these particular topics that we're going to see, right? So without further ado, let's get into it. The whole sequence of videos surrounding these concepts are very easy, as long as you follow the protocol that I've put in place, and if you practice actually a couple of problems, this becomes very easy. So the first topic we're going to look at is Fischer projection. Now, what is Fischer projection? I think I just mentioned that just a second ago as to why we learned this. Is most of us, or actually some of us, can actually visualize a molecule in three dimension. And that's one of the reasons why Fischer projection comes in perspective, and that is Fischer projection is nothing but a two-dimensional representation of a molecule that's supposed to be in three dimensions. Does that make sense? So let's actually do a problem, because I think that's the only way you can actually understand this concept. So you're all familiar with this, right? We learned this. We learned how to determine R and S. Okay? There are some rules, however, and these are pretty generic rules. Assign number to all carbons in the molecule. Doesn't matter, you start from left to right or right to left. Now, this is important because we're going to draw more like a spinal cord structure, and for that we really need to know how many carbons we have in the molecule. And then we are going to determine R and S for this molecule that you see right now, and then we're going to overlap that same R and S format onto our Fischer projection when it's all said and done. So that should be our second task, and you're determining R and S for the structure shown here. Before you do that, you can actually draw a Fischer projection. And then we will draw a rough sketch of the Fischer projection, and then we will adjust it to actually make the Fischer projection the correct format. Okay? Now, all of these might seem like I'm speaking French and Latin, but just give me a second. All of these will fall in place, right? All right, so you're familiar with this little picture from Chem 330. So with that help, let's go ahead and actually assign numbers. Now, I said it doesn't matter left or right, but be consistent for pretty much of the sequence of the videos. I'm going to go left to right. Okay, so you can do the same. So this is 1, 2, 3, and 4. So now I know my molecule contains 4 carbons in the chain, which means my spinal cord would have 4 sort of clamp points to which we're going to work with. Okay, now to determine R and S, it's exactly the same. This is 1, and this is 2, which makes sense, right? And this is 3, and this is 4. So it's counterclockwise, and H is in the front position. So this is an R. Now, this is unique There is a little exception. This may not be a problem at all on the long run, but this is not something we specifically looked at, I guess, after I realized it after I drew the structure. But you can easily make the adjustment, okay? So this is 1, as always. Now the question is, this C is attached to C here and C here. And this one is attached to OH and then all of the other stuff. This is only attached to a double bond O and a H. Now you might be tempted to think, well, they're both attached to O, but then this is attached to this, so this should be 2. No, this C is attached to a double bond O. Okay, double bond O takes precedence over single bond OH, which is why this is 2, this is 3, and this is 4. So that means it's clockwise, right? And front, which is S. So we've done 2 things. We've assigned numbers to determine how many carbons we have in the chain, and then we determine R and S like we regularly do. Of course, this is the only case where this may be something you have to adjust, which means if you have 2 carbons, one attached to OH and the other attached to double bond O, you have to give priority to the carbon containing the double bond O, because if you go back and look at our priority chart from 330, double bond O takes higher priority over single bond OH. All right, now comes the actual part, which is Fischer projection. So we have 4 carbons, right? So put 4 dots first. I'm sorry. It's been a while I've used this. So 1, 2, 3, and 4. So that means draw a straight line. Okay. I'm not going to do a great job, but you know, you're getting the drift. Oh, basically it's missed. Oops, sorry. It missed the dot, but that's our spinal cord. Okay. The second, since I went from this way to this way, I'm to be consistent, so I'm going to keep 1 here, 2, 3, and 4. Okay. So 2 is where my first chiral carbon is, right? So 1 is basically, it's got, this is a carbon, right? This is CH2OH, right? So this C, just write C, and it's attached to, you know, CH2 and OH, right? That's basically what this is. You can erase I just went a little overboard on my spinal cord, but you understand it, right? That's 1, which is CH2, and then this OH, just right there. Now for 2, write a flat line. Now that's our second carbon. Now it doesn't matter whether you put the H on the left side or right side, but be consistent with me. I'm always going to put my H on the left side. Again, it doesn't matter, but if you're consistent, you can eliminate a lot of the issues. I'm going to put the OH on the right side. Similarly, I'm going to number 3. It doesn't matter. This H, whether it's in the front or back, has no implication when you go on to draw these structures, okay? It's a different pattern. So again, coincidentally, the H is on the left side here, but this has no bearing, okay? And it doesn't matter whether it's in the front or back position. Just pretend H is on the left side, okay? And the OH is on the right side, okay? And then this is the 4th carbon, which contains the double bond O. So again, I went a little bit. You can always minimize how far you go past the spinal cord dot. So this is C double bond O. Of course, is also attached to a hydrogen, right? This is a basic Fischer projection. Now we comes to the part where we have to make sure that 2 and 3 are R and S again, okay? Now this is where it gets very tricky but easier. I assigned H to the left side, right? Always assume this hydrogen is always in the front position, okay? Now go ahead and draw these, convert them. I'll tell you why, because it just makes life easy, okay? Assume they're in the front position, okay? So now again, start numbering for this carbon because this is the chiral one. So this is 1, Again, they're both attached to C, but this is also attached to all of this stuff. So this is 2, this is 3, and this is 4. Okay, so connect these dots. So it's clockwise, right? And front, clockwise front is S, right? But was 2 an S? No, it was an R. So what we have to do now is we have to redraw. Sometimes my pen doesn't read right away, so I apologize for that. So I'm not going to go further. So because we got S, we assumed hydrogen is in the front always, and we did our math, and it's clockwise front, which is S, but we should have R, right? So what you need to do is when you draw the OH on this side and the H on this side. That's it. Now let's go to this side and then do the same math. So again, 1. Remember, they both attached to C, but this is attached to OH. This is attached to a double bond O, so this gets priority. 2, 3, and 4. So it's 1, 2, 3. Again, this is counterclockwise, right? Sorry, 1, 2, 3. This is clockwise as well, and this is front, and that's S. Well, we got S here, so we shouldn't have to change anything. Leave it as it is. H, OH, and then you can extend it further and leave this as it is. Now, if you notice something, the things that are always in the vertical, okay, that is not the ones. This is how you most likely will get it on the test or quiz or homework or anywhere else. So the ones that are always in the vertical position never really have chirality. The ones that are always in the horizontal position are usually the ones indicated to you in your structure with chirality. Okay, and that's it. This is the Fischer projection. You're done. Okay, so there's a few things that you have to observe as you're watching the video. Okay, you may miss a few things the first go. That's why I'm going to keep this example as one video and the second example is another video, so that the video length is short. So if you have to go back again and watch. Play the video, watch for the nuances. Okay, now again, this is not all that difficult. Okay, we've learned R and S, so this shouldn't be a problem at all. Okay, so I'll do one more example and I'll leave a practice problem. Right? So stay tuned more for videos on line to Fischer projection.